Hello student, welcome back to lecture series on Fourier transform. So already I have explained a Fourier transform, Fourier sine transform in my previous lecture along with the example. So if you want to see similar this video, go and check in my playlist. In my today's video, I'm gonna explain to you all some of the example which are based on Fourier sine transform. Okay. So as we have given example here, let's get enter to our example. Find the Fourier sine transformation of e raised to modulus of minus 6. Okay, e raised to minus of mod x here, and hence evaluate. We have to find out the integral 0 to infinity x sine mx by 1 plus x square dx pi by 2 e raised to minus m and m greater than 0. Okay. So this one is a question here. It is a mostly important question, guys, asked in your previous year question papers. Okay. Yes. So let's get started our today's solution with the Fourier sine transformation. Okay. So as we know that formula for Fourier sine transformation. What is this formula for Fourier sine transformation? So Fourier sine transformation, capital F suffix s of a capital S. Okay. We write integral over 0 to infinity whenever we have positive integral. Okay, that means 0 to infinity small f of x sine sx dx, sine sx dx. Okay, this one is our given function, given formula for Fourier sine transformation. Okay, now see that sine sx we don't have to work here, but f of x. Okay, so we want the f of x. That means we have to find out the Fourier sine transformation of e raised to minus of mod x. That means this one is our required f of x. Okay, so what is the value for f of x we have here? E raised to minus of modulus x. Okay, this one is our f of x here. Okay, this one it is our f of x. So replace this f of x here. Okay, replace this one f of x here. But now see that as we have modulus function, as we have modulus of minus of modulus x. Okay, so modulus function means it gives us the positive value and it gives us the negative value. Okay, so which we have to consider here. Now see that as we have interval from 0 to infinity, from 0 to infinity, that means we are going to consider all the value for x which are positive. Now let me explain with the interval here. Okay, so this one is our interval. Okay, this one is a 0, this one is a minus 1 and it goes to the minus infinity. Okay, this one is a plus 1 and it goes to the plus infinity. Okay, yes, this one is our interval. So we have this interval. Okay, so we can see that my 0 to infinity, we want the interval from 0 to infinity. We are not going for the negative, so negative part it is omitted here in our Fourier sine transformation. Okay, so we have to define that modulus of x value. Okay, so mod x means which extracted gives us the positive x also and negative x also. But as we don't have negative values here, so we always consider this x as a positive. Okay, so that means we take always f of x as a e raised to minus of x. Okay, that minus sign as it is here, I'm telling about the value for modulus of x. Okay, so modulus of x can be written as only the x here, as we have all the value from 0 to infinity, that means all the positive values here. Okay, so f of x replace here in our Fourier transformation. Okay, now see that what is the next step coming? Capital F s of s. Okay, this one is a Fourier transformation 0 to infinity e raised to minus x sine x dx. Okay, so this one is the value I just replace here. Okay, so we go for finding the integration 0 to infinity e raised to minus x sine x dx. Okay, so already I explained in my previous lecture one standard formula. Okay, one standard formula for finding the integration. Okay, e raised to ax sine bx plus c dx. Okay, so now see that I'm going to show you all that formula here. Okay, so we are going to apply this formula here. Okay, now see here, this one is the formula I explained in my previous lecture. Okay, e raised to ax can be written as integration of e raised to x. Okay, it can be written as integration of e raised to x sine bx dx can be written as e raised to ax upon a square plus b square a sine bx minus b cos bx. Okay, this one is the formula we are going to apply here. Similar, we have one more formula e raised to x cos bx dx. Okay, this one is also important formula. These are important formula here for solving this integration. Okay, so we go for applying this first formula. Okay, first formula here to this integral. Okay, now see that how I'm going to apply this formula here. So in our next step we are going to compare this one with our given standard format. Okay, so now see that integration over a e raised to x sine bx, so e raised to minus x sine sx. Okay, so compare these two sides and write down another one. Okay, you will get the simplified form of integration directly over here. Okay, now see that e raised to x which is equal to e raised to minus x. So what is the value for a, which is a minus 1. Okay, compare both of them, e raised to x which is equal to e raised to minus x, so value for a which is a minus 1. Okay, sine bx, what is the value for b? It is yes. Okay, b which is equal to yes. So replace a as a minus 1, b as a yes. Okay, yes, replace a as a minus 1, b as a yes everywhere in our given solution. Okay, this integrand. Okay, so you will get the simplified form. Okay, now see that how I'm going to replace these values here. Okay, so integration 0 to infinity e raised to minus x sine x dx. Okay, can be written as e raised to x. E raised to x means e raised to minus x. Okay, e raised to x means e raised to minus x power to the power minus x. So a square plus b square, minus 1 square it goes to plus 1, b square means a square. Okay, that means a square plus b square. Value for a minus 1 sine, what is the value for b? Yes x. Okay, value for b it is yes, x that is minus value for b which is a yes sine. Okay, a sine bx minus b cos bx. Okay, so value for cos, keep cos as it is. Value for b it is here yes cos yes x. Okay, this one is the simplified integral. Okay, so as we have integral 0 to infinity, limit as a 0 to infinity, you have to replace limit as the 0 to infinity into the our calculation. Okay, so don't forget to replace the limits. Limits are very much important here. Okay, so we write e raised to minus x upon 1 plus s square minus sine sx minus s cos sx. Okay, yes, now what we do, we replace infinity wherever you get the x here. Okay, as we are integrating with respect to x, so replace x as infinity minus replace x as a 0. Okay, so first what we get in the replacement of infinity, now see that e raised to minus infinity. E raised to minus infinity means, I will explain to you all here, e raised to minus x. Okay, e raised to minus x, it can be written as 1 upon e raised to x. Okay, 1 upon e raised to x. I am writing e raised to minus x as 1 upon e raised to x. So replace that infinity. Okay, as I am going to replace infinity here, replace that infinity minus 1 upon e raised to infinity. Sorry, 1 upon e raised to infinity there. Okay, and e raised to infinity means it is the biggest term, that means 1 upon infinity, and we know that 1 upon infinity it is 0. Okay, e raised to infinity means e which is having value. What is the value for e here? E has the value like a 2.71 something like this. Okay, so to the power, if you consider infinity, then we get this one as the infinity term, and 1 upon infinity it gives us the 0. Okay, yes, so when we replace x as a infinity, numerator goes to 0. Okay, 0 upon 1 plus a square, it also goes to 0, and 0 multiplied by entire term, it goes to 0. Okay, that means when we replace x as a infinity, we get the first term 0, entire this term 0. Okay, yes, so if this term 0 minus, okay, 0 minus, replace wherever you get x as a 0. Okay, so x it is a 0, e raised to 0 which is a 1. Okay, so we write 1 upon 1 plus s square. Okay, we write 1 upon 1 plus s square. Okay, yes, so minus sine s 0, s into x is a 0, minus sine 0 it is a 0, so it is a minus 0. Okay, minus s cos 0, cos s into 0 means cos 0 which is a 1. Okay, so 1 into s, it remain only the s here. Okay, yes, so what we get, our next step, multiply minus under bracket here. Okay, 1 upon 1 plus s square into minus s. Okay, minus and minus, it gives us the positive. So let me write one step separately, 1 upon 1 plus s square. okay, 1 upon 1 plus s square, okay, and minus s multiply here, bracket complete, okay, minus minus goes to the plus. So we write next step, this complete integration of a Fourier sine transformation over s, okay. So we write s upon 1 plus s square, okay. This one is your required Fourier transformation, okay. I hope you all have understood this Fourier transformation here. So this one is our required Fourier transformation for e raised to modulus of minus of modulus x, okay. So we have connected part for this question, which is a 0 to infinity, x sine mx upon 1 plus x square dx is a pi by 2 e raised to minus m, okay. So for finding this solution, now see that we have some f of x into sine mx, okay. That means it seems like that we have to apply inverse sine Fourier transformation, okay. What we have to apply? We have to apply inverse Fourier sine transformation, okay. And inverse Fourier sine transformation it written as, okay, let me write inverse Fourier sine transformation f of x, okay. This one is a small f of x is the inverse Fourier sine transformation for capital F of yes here, okay. Yes, we write a 2 by pi, okay, 2 by pi integration over 0 to infinity Fourier transformation f s of s, okay. This one is a Fourier transformation over s sine sx dx, sine sx ds, okay, sine sx ds. This one is our sine, okay, inverse Fourier sine transformation formula, okay. So we have to replace value over here, so we'll get this step here, okay. We have to derive this step here, okay. Yes, as we have f of x, what we have f of x in our example, f of x is equal to e raised to minus x, okay. We are taking interval 0 to infinity, means modulus gives us a plus x value, so minus it is there, so e raised to minus x as our given f of x from our example, okay. So replace f of x here, e raised to minus x, okay. F of x is a e raised to minus x. 2 by pi we are not going to do any changes here, 0 to infinity here, okay. Yes, now we want the Fourier transformation of es, okay. So we want the Fourier transformation of es that we found it earlier, s upon 1 plus s square, okay. So replace here s upon 1 plus s square, okay, s upon 1 plus s square. This one is a Fourier transformation, and the sine sx, okay, sine sx ds keep as it is, okay. We are not going to do any changes over here, okay. Yes, so e raised to minus x I replace here. Now see that what we have in this part and compare this one with this one, okay. So we can see that e raised to minus x, instead of x we have m, so replace x as a m, okay, replace x as a m, so we get the e raised to minus m here, okay. Take pi to the other side, 2 to the other side, we get the pi by 2 here, okay. Replace, what we are going to do now, see carefully here, we are going to replace x as a m, okay. We are going to replace x as a m. Why I am replacing this value? As we have in our proof given e raised to minus m, so we have e raised to minus x, so replace x as a m, so e raised to minus m. So 2 by pi, take it to the other side, we write pi by 2 here, okay. So 2 by pi can be written as pi by 2 e raised to minus m, okay. So integration over 0 to infinity 1 upon 1 plus s square, okay, sine s x replaced by m here, okay, x replaced by m, so sine s m ds, okay. Yes, sine s m ds. Now see that, so we got the value, okay. So what we got the value here, pi by 2 e raised to minus m here. So x upon 1 plus x square, sine s m ds it is there, okay. So we have to this one is yes, this one is yes, don't go for any mistakes. This one is s upon 1 plus s square, sine s m ds, okay. Now see that our integration, okay, is in the form of ax here, okay, dx. So what I want, I have to replace all the term in the form of yes, as we have yes it is here now, so I'm going to replace that all the term in the form of x, so we'll get directly the value here, okay. So we know that, so I'm telling you all one short result that can be helpful for you all, okay. Integration of x square dx it is there now, so we can write this one as an integration of s square ds. Okay, both are equal here, both are equal. I just replace their variable x square as x as a s, so dx replaced by ds. Okay, same this quantity, this type of the integration I am applying here. Okay, this one is just for your understanding, guys. This is not the part of solution, this one is for your understanding. So integration of x square dx can be written as integration of s square ds. Okay, yes. So pi by 2 keep as it is, e raised to minus m keep as it is, 0 to infinity keep as it is, s replaced by x, x upon 1 plus x square. Okay, sine x into m dx. Okay, now see that one exactly we have to prove here. Okay, so what we have to prove here, prove here in our example, pi by 2 e raised to minus m 0 to infinity x upon 1 plus x square sine mx dx. Okay, this one is our required proof. Okay, so that we have to prove here. I hope, guys, you all have understood my solution. Okay, it is one of the easy solution, guys. Okay, such a questions are coming for your Sppu question paper for 4 to 5 marks. Okay, I hope you all have understood this solution. So even after, if you found anything difficult, guys, let me know in my comment section. I'm putting lot of efforts for these examples. I just want to deliver all these my lectures to you all. Okay, so even after, if you found anything difficult, guys, let me know in my comment section. I will come up with the similar videos. And if you want more videos, if you have any doubt related to such examples, let me know in my comment section, guys. For you all, I will upload similar video in our channel. So thank you everyone, thank you for my today's lecture.